Hi, this is Christopher Boucher, and I'm going to review how to do a hypothesis test with a z-distribution, and it's a two-tail test. So it appears to be a little bit more complicated, but it's actually not too hard. Okay, I'll get started. This is very similar to a previous question, except this time it's written in a way, or it's set up in a way that we're not sure if they're making more or less. So you might do a two-tail type of test when we're not sure what the results are actually going to be like. So the average annual salary for a starting plumber in the United States is $40,000 with a standard deviation of 500. A sample of 32 new plumbers shows an average annual salary of $40,200. Based on this data, are new plumbers earning a significantly different amount than expected? So in this case, the prior question or example that I went over had a more. This one says different. So we're trying to figure out, are they earning more or less? Well, it looks like they might be earning more, but we're not sure. So when we do a two-tail test, what happens is we're open to the idea that it could be high or low. And I'll show you kind of how the difference is. Okay, so similar to the last one here, let's see, our null hypothesis is going to be 40,000, except in this case, our null hypothesis is actually HO equals, it's actually mu equals 40,000. And then our alternative hypothesis is mu does not equal 40,000. So this is a good example of the difference between one tail and two tail. And then our mu is still 40,000. So a lot of this data is the same as the last time, except we're just doing a two tail versus one. Our standard deviation is 500. And our x bar is 40,200, and our n, which is our sample size, is 32. Okay, so similar to last time, let's see, we have a known sigma, and we have n is greater than or equal to 30. Therefore, we will use the z distribution. So our level of significance we're looking for is 2%. So this is the big part of the reason why we're doing this two-tail example here. So it's 2%. Now, we could look this up on the table and find the one that's for 2%. But if we're doing two-tail, we're open to the idea that it could be higher, it could be low. Of course, it looks like it's high because of our sample mean is a little bit more. But let's do a two-tail and do this. So when we do the two-tail, and it says a 2% level of significance, or alpha, our whole test cannot have an alpha value of more than 2%. And when we spread that over two tails, we have to take that 2% and divide it by 2. So we have 1% per tail. And so what we do is we look up on the table the value for each tail. For each tail, so that we can do 1% in each tail. So we're going to look for the z-score for 1% alpha for each tail. And the other thing is, when we have this, when our inequality for our alternative hypothesis is not equal to, what that means is we have a two-tail as well. And the big deal about the two-tail is that this part right here, it says different, or it says, it doesn't say more than, it says or less than, it says something like different. And what that means is it's not the same as the status quo, it's not the same as the null hypothesis. So we know that it's a two-tail, which means the person doing the test technically wouldn't know which direction the results are going to go. Okay. So let's take a look at our table. So we want to get the value for the for each tail, and once we add this up, it cannot equal more than 2% for both tails. So what we do is we want to find the essentially the value under the curve that will give us 1% in each tail. So when we look this up on the table, and we look for, now this table essentially has, in this case, all of the beta. So this has all of the beta values. Now, what I know, because I set up this question, what it is it's 2.33. Now, let's take a look at this value. It is 0.4901. So if we have 0.4901 as the beta on each side, which means it's the part that's kind of in the middle of the distribution, that leaves us with about 0.01 on each tail, which is what we're looking for. And that's what I have written down here. So we have right here, two-tail hypothesis, 2% alpha, which is actually 1%, 1%. You add that up, and then the 98%, which is our beta. And so this right here, 2.33, is the value that we're going to have as our cutoff value for this rejection zone method. Okay. So what we do is we put it right here. Now we can put negative. Negative shows directionality. So negative 2.33 and then 2.33. It's only the absolute kind of difference or direction from the mean, that negative. It shows us which way we're going. Okay, so now we know what our rejection zone cutoffs are. So let's do our Z real quick. Now this is going to be the same as my one-tail example. So I already have this laid out, but let's do this. Which is actually, what's that, 40,240. And then sigma is 500. And that's what, 32. Okay. So I have already solved this. The answer here is the answer is 2.262. Okay, so we have to figure out where we're going to put this. Is it going to be in the shaded rejection area or not? And as I mentioned in my last example, as we move further away from the middle, which is our mu. Now, if we're looking at this as standard deviations, this is the center. But if we're looking at this with the actual values, this would be our 40,000 as we go out. So as we go out, the number increases. Standard deviations away from the mean are increasing. So 2.26 versus 2.3, we know that this value is going to be inside the non-rejection zone area. And what that means is our answer is do not reject H0. Sometimes we say HO, but H0, which would mean that the plumbers might actually be making what we thought, which was $40,000 a year on average. So the reason why we did this question and we kept it very similar to the one-tail, there's a couple reasons here. One of them is if you watch the one-tail one, you're like, yeah, we know that they're making more because in that example, we rejected the null hypothesis and we said that they may be making more money. But when we go and we change to a two-tail, suddenly our alpha is changed, and the number, our cutoff value, goes from 1.96 up to 2.33. Now suddenly we're not rejecting our null hypothesis in this one, and it kind of illustrates that if you pick the wrong test or you manipulate the test, we can get the results that we want. And this is a common occurrence in everyday world where we can manipulate the numbers to make it so they work. Scientists who are trying to get certain results can manipulate it that way. Okay, thank you for watching.